Hey guys, welcome to section 1.2. I feel like 1.2 is a pretty good sequel to 1.1 because in 1.1 we learn about what limits are and the basic ways to solve them. And I feel like in this section we just start to dig a little bit deeper. I have a pretty good feeling but by the end of this section you have a good grasp on how to solve the majority of limits. And so the first thing I want to mention is that there's three main ways to find limits, three techniques. So the first technique, I'm going to write it down, is the graphical method. Graphical. And basically all that the graphical method is, just looking at a graph and then determining from the graph what a limit does. So let me kind of show you a quick example, and I'm sure you'll definitely remember this. So x, y, and let's say we have that super easy example of like y equals x squared, right? So we have something goes up right here, and then something that goes up right there. And let's focus on a certain point, let's say a value of 3. It's going to correspond to y value of 9. Obviously not drawn to scale, but oh well. And then you just look at that point and then see what happens on the left hand side, and it goes to that value of 9. And happens what on the right hand side also goes to the value of 9. Then you could say that the limit as x goes to 3 of x squared will be equal to 9. And so you can find that out just by looking at the graph. Pretty chill, right? The second method is what's called the numerical method. Numerical. And this is basically just setting up a table or any list of values or numbers like that, and then determining from that list of numbers basically what the function comes to and what the limit is equal to. And that's when we got Desmos or got your graphing calculator, set up a table, and then figured out those values. And it's not quite as visual as looking at a graph, but it's still not too bad because you can just look at the list of values and then see what happens. The third method, I would say, is probably the most involved, but also in some ways a little bit easier than the other two because you don't have to do as much, and that is the algebraic method. And so basically, as I'm sure you can tell by the title, you just use algebra to be able to determine a solution and find out what your limit is. So let's take this example again of x squared, right? So we have limit as x goes to 3 of x squared. And how do we find this? Without looking at a graph, without looking at a set of values, and to be able to determine this. So here's where I want to introduce the very first principle of finding a limit algebraically, something called direct substitution. I'm going to get another color for this because this is pretty important. Put it in red. That way it's pretty emphasized, right? So direct substitution. I'm just going to call it direct sub or DS. So whenever I'm solving a limit and I use the acronym DS, always know that I mean direct substitution. And basically what it is, it's basically just plugging a number in. And so this 3 right here, we're going to plug it in like we're plugging it into a function. We're plugging in for that x, 3 squared, and that's going to be equal to 9, right? I'm going to switch back colors. Not too bad, right? And so basically all you do is just plug in a value, and then you might be thinking, well, why haven't we done that all along? Pretty simple, right? Well, the reason why we introduced the graphical method is I wanted you to know, and the person who wrote the book wants you to know, how limits work and exactly why we're doing it and what really goes on when you look at it as a picture, as a graph. And then numerically, we wanted to show you just because so you can kind of see the intuitive sense behind looking at numbers and all sort of that. But whenever you're solving a limit practically, this is probably the best way to go. Then you might be saying, well, solving limits is pretty easy, right? Well, it gets a little bit harder. Just like graphically and numerically, it got harder as far as analyzing certain things did. It can get harder algebraically. Let me show you another example. Let me show you, let's find a limit as x goes to 2 of x squared minus 4 over x minus 2. And so here, let's try direct substitution again. And so let's use ds. And for that, what we're going to do is we're plugging 2 everywhere there's an x, just like we do with the function. So 2 squared is going to be 4, 4 minus 4, and then here we're going to have 2 minus 2. So here you'll see that we have 0 over 0, and that's actually not something that you can calculate. This is actually something called an indeterminate form, which we'll learn a lot about in the future, but we can't really do anything to this. So what do we do? Because direct substitution didn't work because in the previous example we got a nice number, so what do we do here? Well, the thing with the algebraic method is possibly we can look at this right here and possibly do something to manipulate this expression and maybe we can kind of cancel some things out, maybe we can make it a little bit more clear. And so when you look at something like this, what can we do? So when I look at something like this, I kind of look at the top right here, and I'm like, you know what? X squared minus 4. I feel like there's something I learned in algebra that might be helpful to help me with that. And there's something called the difference of squares method. I'm sure you've probably seen this before, that when you have, let's say a and b, when you have a squared minus b squared, remember both of these are squared, this is equal to a plus b times a minus b. This is a property you learn in algebra. If you want me to do the proof, I can do it for you, but I don't think it's really that necessary. But that's just a method that we learned. And so we can actually apply it to this because x squared, we know this is squared, but 4 is also a square. It's a square of 2. 4 is the same thing as 2 squared. So we can write it like this, that x squared minus 4 over x minus 2 can be rewritten as x plus 2 times x minus 2 all over x minus 2. And you see here, if you put parentheses around here, it might be a little bit easier to see that these two are actually the same, so they can cancel out since both of these are multiplied to each other. So you can do this, this, and what we have left is just x plus 2. And remember, we're taking a limit, right, as x goes to 2. So let me bring it right up here. So we're taking a limit as x goes to 2 of this expression, but remember, it turns into this, so I'm just going to write this now, x plus 2. And let's try direct substitution again. So I'm going to plug in ds, and what do we get? Well, we get 2 plus 2, which is just equal to 4. So remember, the first time we came up with a 0 over 0, which we couldn't do anything with. But when we just did a little bit of algebra to it, then we found out with 4. And so that's an example where at first it might seem like it's not that hard, but this is way easier than looking up a graph or setting up something, setting up a table. You're basically just using a little bit of algebra. All we did is we just did this method, this theory that we learned from algebra, plugged that in, and then we were able to find our answer. It's not that hard. And so next thing I want to mention, whenever it comes, let me just start a new page here. Whenever it comes to solving limits algebraically, you always want to be careful of when something is going to be undefined. So in that case, we had something divided by 0. In other cases, we're going to have maybe a square root being negative. And I'm sure you probably remember, like if we were to take the square root of, let's say, the limit as x goes to -5, for example, of the square root of, let's just say x. Keep it nice and simple. Well, here if we plug in -5 in, we can't really do anything to it. So that's an example of something that will be undefined, and then we're going to have to do additional stuff with. And then you'll find out later different ways you can solve things like that. But there are going to be different cases where you're going to have something that's undefined, and then you're going to have to learn some algebra to be able to get through it. With square roots, I would recommend using something called the conjugate, and we'll definitely go over that when we do the homework problems. I don't really want to focus too much on it now, because that's something that we can definitely do later and focus on later. Obviously, if you have any questions, I'd be happy to help you out with it. But the next thing I want to mention is this really important theorem. So all those problems we'll get to later. Don't worry about it. We'll definitely get to it. But one thing I want to mention, as really kind of a byproduct of all these algebraic rules, is something called the Squeeze Theorem. Squeeze Theorem. So the Squeeze Theorem, as its name might imply, is basically a theorem saying that if you have one function and another function that you know, and you know the limits for a certain value, and then if you say that you have this other function that you don't really know how to evaluate limits and any that sort of stuff, if it's squeezed between those two functions, then you can say that the limit is equal to these other two limits. And that might sound like a whole bunch of math mumbo jumbo, so let me give you an example. Let's say this is our x and y, right? So this would be x, this would be y, and let's say we have the example of x squared, for example. So I have this function right here, right? And let's say also that we have another function that is going to be this line, right? I'm just going to call it like this. And let's say it's kind of hard to see it, but for this, there's going to be this one tangent point that it is actually, I'm going to say it goes to the origin. This is drawn pretty badly, I'm sorry. But through the origin, it actually intersects at the exact same point. But it doesn't intersect anywhere else. It might seem that there's this whole area where it intersects. Actually not true. The function of x squared just goes straight up here, and the line just goes straight through here. So what's my point? Well, let's say there's this other function. That's just this weird function. We don't really know it. And so I'm going to mark it with a different color. And let's say that it kind of goes like this, and then but it goes through this point, and then it also goes through here, something like that, right? And so we don't know this function. I'm just going to call it g of x, and then these other two, I'm going to call f of x, and this one I'm going to call h of x. So we know f of x, we know h of x. And so one thing that we could say is g of x might be this function that we have no idea how to find the limit algebraically or how to find it in other ways. But we can say is that if the limit, if we can show that this is trapped between these two, and that we want to find the limit at this exact point, if it's trapped in between these two, we can logically say that this limit has to be equal to the limit of this one and the limit of that one. And that might seem like it's super intuitive, but there's a lot of different cases where it can be super helpful. And just to kind of illustrate it, I want to show you an example. So let's find, first of all, let me just separate it through a line. Let's find the limit as x goes to 0 of x squared times the sine of 1 over x. So this is where we start incorporating a little bit of trigonometry. And I feel like that can be really helpful, but trig problems can also get pretty complicated depending on how far you go. And so this function, we don't really know what to do with. We don't really know like how to solve it or how to go down whatever road we need to go down. But one thing that I'll say is that let's take this x squared away for just a second. And what is the limit as x goes to 0 of the sine of 1 over x? Now, we might not know limits super well to find out trigonometric functions, so let's even just take the limit away for right now. Let's take the sine. And if you know trigonometry, you would know that if you take the sine of any value, it doesn't matter if it's 1 over x squared, whatever, you name it, the sine always has to be in between -1 and 1, right? So could we say, by sort of deduction, that -1 has to be at the left-hand point of sine of 1 over x. And that has to be less than or equal to the positive one, right? Because this value of sine always has to be in between these two values. And if you don't know how trigonometrically a sine value has to be in between -1 and 1, I'll just say just review your unit circle and just kind of review that sort of trigonometric knowledge. It's just trigonometry is a prerequisite for this class, and I feel like it'll definitely do you good to know that sort of stuff because you definitely need that sort of stuff to solve these sort of problems. But we do know that from trigonometry, right? And so now when we're looking at this sort of value, let's do some algebra, right? So remember this x squared that we left out? Let's put it back in. So let's multiply everything in here by x squared. And the way that inequalities work is if you multiply by 1, you have to multiply by all of them to make sure that it's a consistent value. And so in that case, what we get is negative x squared less than or equal to x squared sine of 1 over x less than or equal to 1, right? And so what we know here is that this value, if you think about it, has to be trapped in between, oh, I'm so sorry about that 1. It's actually x squared because I multiply x squared by 1. Sorry about that. And so what we have is negative x squared here at the left-hand side and x squared here at the right-hand side. And according to this inequality, this whole value of x squared sine of 1 over x has to be trapped in between these two values because we created this inequality. And so when I say trapped in between two values, maybe this theorem comes to mind. And the way we do it is we know the graph of negative x squared, right? And we know the graph of x squared. And so let me just draw this graph real quick. First thing I'm going to do is I'm going to delete this left-hand side so we can use this stuff. All right. And delete that. And delete this a little bit. Perfect. And so let's move the graph over here. And let me create this graph here. Oops, I was supposed to create a line. Oh well. At least one line was good, one line kind of sucked. It's all good. So this is going to be y, right? And this is going to be x. And so the sine function, we would know, especially when it has something like this, it's going to have some sort of curves, whatnot. We were not entirely sure what it does, but let's draw these two graphs right here, negative x squared and x squared. So for x squared, it's going to go something like this. We've drawn this graph a few times now. That is a horrible parabola. Wow, that is bad. But it'll do justice. And then on the right side, we're going to have negative x squared, which will go like that. And I know it might be kind of hard to see from my horrible drawing, but this is basically just a mirror image of this. So the x squared function goes like this, and this is f of x equal x squared. And then down here, I'm going to call this g of x equal negative x squared. And so basically we have this function that goes straight up, this function that goes straight down, and logically, according to this inequality, we know that this function is actually trapped in between here. And so I'm just going to draw it in red real quick. And so it's going to probably rotate something like this, like a sine function does, and always has to be between -1 and 1. And it's going to go through here, and then probably going to do something like that. I'm not entirely sure exactly what it does, but it doesn't really matter. But we do know that actually all three of these functions go through the same point of 0, 0. We know that. And so basically what we can say, according to the Squeeze Theorem, is let's take the limit. What is the limit as x goes to 0 of f of x? And f of x, remember, is x squared equals x squared. And so what is that? Well, if you just take the limit from the left-hand side, it goes to 0. Limit from the right-hand side also goes to 0. Also, you just want to plug it in, direct substitution, 0 squared is 0. So this is going to be equal to 0, right? And let's take the limit as x goes to 0 of g of x, which is equal to negative x squared, right? And that is also equal to 0, because it doesn't matter if you put the negative or the positive. If you plug in 0, it's just going to be 0 all the way. And so we know that both of these are equal to 0. And logically, according to the Squeeze Theorem, since this third function is trapped in between, and then we're evaluating the limit at 0, we can say that the limit of x squared sine x, or sine of 1 over x, sorry, as x goes to 0, also has to be equal to 0 according to the Squeeze Theorem. That's basically that formula. And so this formula might seem a little bit on the complicated side because there's a lot of different things that you kind of have to go over. And trust me, we'll do problems with the Squeeze Theorem. Don't worry about it. We'll get to the more complicated problems. I just want to show you what this theorem is because it actually has so many different applications. I remember when I was taking multivariable calculus, which is third semester calculus, or third year calculus, depending on if you take it in high school. And if you do take this class in high school, kudos to you. I'm not that smart. If you take multivariable, you'll find that you actually do use the Squeeze Theorem in certain examples. I remember doing some problems with integration and differentiation, which are concepts that you'll learn later on, and I actually had to use this theorem, and so it actually shows that it actually is useful. So I want to end this video with just two more things, and trust me, I'll make it super quick. And these are two sort of formulas that would be good to memorize, good to know, because you can kind of manipulate these formulas to be able to solve more complicated limits. And both of them actually use the Squeeze Theorem as part of its proof, but the proof is like super long, and I would say I didn't learn the proof when I first learned this class. I kind of learned it later because I found it was interesting, but that's just me as a math nerd. I would say there's no need to learn these proofs. Just know that these kind of stem from the Squeeze Theorem, and you can use these formulas to be able to solve more complicated limits, and they both pertain to the concept of trigonometry. So the first one is if we take the limit, and this is just a good thing to know, as theta, so theta is a Greek letter, which I'm sure you've probably seen before in other places. It basically usually pertains to an angle. You probably see it a lot in geometry when you're looking at different angles, stuff like that. As theta goes to 0, and just want to let you know, you don't have to use theta. You can use x, but I just want to say that theta is a good thing to remember it by because theta always represents angles, and that's what this formula does. So when we have the sine of theta, so it's basically the sine of some sort of angle, we have the sine of theta over theta. So you could write this as the sine of x over x, or the sine of whatever. Any sort of variable you want to put in there, it's always equal to 1. So remember, the proof for this is pretty long. You have to do all these sort of different things. If you thought the last problem was long, This is way longer than that to solve that. This is just a good thing to know. So this is our first property. And the second property, give you a different sort of magenta. The second property is if we take the limit of, as theta goes to 0 as well, of the cosine, not the cosecant, sorry, the cosine of theta minus 1 all over theta. That is equal to 0. So remember, the formulas, the proofs, to be able to solve these, pretty long, but these are just two really good things to know. I would say definitely memorize these, definitely know them, because in the problems, especially when we do trig problems, and I'll definitely make sure that I include trig problems when we actually do the exercises, that these are super, super important and super good to know, especially when solving trigonometric limits. So that's it for this lesson. I know that's a lot, different techniques for solving limits, and I know that you probably have a few questions. I purposely didn't include a super, super in-depth analysis of this section because I feel like a lot of it just comes from doing the problems. Because this section is all about doing problems, and I feel like as you do more problems in the next couple of videos, and I'll show you how to do those, I feel like you're going to get a really good grasp on how to do these limits. Alright, see you next time.